Hello viewers, welcome to online course on Mathematics 3. This course is basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the continuous distribution function and probability density function, and some related examples we will discuss in today's class. So myself, Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is the details of my contact information. Whenever you find any difficulties regarding today's class, you can contact freely or send message with my mail ID. And my mail ID is sanjay.vishwas@gnit.ac.in. So before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the probability distribution function and the discrete distributions. So in the previous class we have discussed about the random variables and the distributions function, and after that we have discussed about some properties of distributions function as well. And then we have talked about the probability mass function and discrete distributions, and some important discrete distribution we have discussed in the previous lecture. Then we have talked about some important examples on discrete distributions. So today we are going to discuss about the continuous probability distributions, and this is my third lecture on probability theory. So here is the content of today's lecture. So first of all we will talk about the probability density function on the distribution function, and after that we will study on the continuous distribution as well. Okay, so after that we will talk about the some properties of the density functions. So and then we will discuss about some important continuous distributions as well. So in that section where the continuous distribution are the uniformity distributions and the normal distribution and standard normal distributions as well. So they are the continuous distributions and we will discuss in this lecture. So after that we will talk about the transformation of a random variables. So in that section where the transformation from fx to fy, so there are two density functions fx and fy for the variables x and y. Okay, so there is a transformation from x to y on the continuous distributions. So after that we will talk about some important or examples on continuous distributions. So first we will begin with the probability density function. This is the definition of the probability density function. Okay, let capital X be the continuous random variable with the distribution function fx is equal to probability of minus infinity less than x less or equal to small x. So this is the definition of the distributions function, Then the function small fx is said to be probability density function or PDF in short of x if fx is integrable on the interval a to x, where x is a variable, okay, for all values of a, and if fx is equal to integration over minus infinity to x f of t dt. So this is called a probability density function, where a small fx is a probability density function and this function is integrable on the interval a to x, where x is variable and a is a fixed number. Okay, so then f of x, capital Fx is equal to, in that case where fx is equal to integration over minus infinity to x ft dt, and this hold for every value of x, and x is a real variables. Okay, so in a discrete case, the f of x is equal to summation over I is equal to minus infinity to x or plus infinity f of I. Okay, but in a continuous case where the function is integrable in the interval, whole interval a to x, and in that case the function f of x is equal to, this is the distribution function, fx is equal to minus infinity to x f of t dt, and this function is continuous in that interval. Okay, and it is hold for every value of x. It's called a probability density function. So after that we are going to talk about the continuous distributions. So the distribution function f of x of a random variable capital X is said to be continuous if capital Fx is continuous and its derivatives f dash x is piecewise continuous everywhere. So piecewise continuous means the function is continuous in any subinterval of a finite interval. Okay, so if the interval a be divided into a number of subintervals, okay, or a finite number of subintervals, so each of these intervals the function is a integrable functions. So if fx is continuous and its derivative, that is f dash x, and this is actually the piecewise continuous function everywhere, and in that case probability of x is equal to a, and this is equal to fa minus f of a minus 0. And you know, in a probability density function or in a continuous distribution, so you know, in a continuous distribution function, the fa minus f of a minus a, and it is equals to 0. But in a discrete case, this is not equals to 0. So if the function is continuous in the whole interval and it is differentiable also, that means f dash x is differentiable, and f dash x is also exist and is continuous piecewise in any interval. So therefore probability of a less than x lesser equal to b, and it is equals to, you know, this is the distribution function, definition of distribution function, and this is equals to fb minus f of a. So fb minus fa in a continuous case, and it is equals to integration over a to b f dash x into dx, and you know f dash x is equal to small fx, so this is equals to integration over a to b fx dx, where fx is equal to f dash x. So this fx, small fx, is called the probability density function of the random variable capital X. Okay, so in a random variable capital X, small fx is called the probability density function, and it is satisfied probability of a less than x lesser equal to b is equal to integration over a to b fx dx, and where fx is equal to f dash x, capital F dash x, and capital F dash x is piecewise continuous everywhere. Okay, so also f of x is equal to probability of, you know, this is the definition of the distribution function. So in a distribution function, fx is equal to probability of minus infinity less than x lesser equal to small x, and it can be written as, in a continuous case, integration over minus infinity to x f of t dt, and if we put x is equal to plus infinity, then from this integration we will get minus infinity to plus infinity f of t dt is equal to 1. That means when we put x is equal to infinity, and from this integration we will get minus infinity to plus infinity f of t dt is equal to f of infinity, and you know, f of infinity is equal to, there is a properties of the distribution function I have already mentioned in the previous class, where f of infinity is equal to 1 and f of minus infinity is equal to 0. So from this we will get integration over minus infinity to plus infinity f of t dt is equal to 1. Okay, so after that we will talk about some important properties of the density functions. So number 1, if the function fx is a probability density function of the random variable capital X, then f of x is greater or equals to 0, and integration over minus infinity to plus infinity f of t dt is equal to 1. So these two are the very important or the fundamental properties of the probability density function. Fx is greater or equals to 0, that means probability density function is always greater or equals to 0, and integration over minus infinity to plus infinity ft dt is equal to 1. So here is the proof of the first properties. So from the definitions of the continuous distribution, f dash x is equal to f of x, where f dash x is piecewise continuous in any intervals. Okay. So since fx is an increasing function, so f dash x is greater or equals to 0. Okay. So f dash x is greater or equals to 0, that means f of x is greater or equals to 0. And since f of infinity is equal to 1, so from the definitions of the continuous distribution, integration over minus infinity to plus infinity, f of dt is equal to f of infinity, and f of infinity is equal to, so this is the properties of the distribution function. F of infinity is equal to 1. I have already mentioned in the previous class. So integration over minus infinity to plus infinity, f of t dt is equal to 1. So these two are the fundamental properties of the probability density function. Okay. So after that we will move on the next properties of the density function. So for a continuous distribution, probability of a lesser or equal to x lesser or equal to b, and it is equals to integration over a to b fx dx. That means fb minus fa. Similarly, in a continuous distribution, we can find the probability value of a less than x lesser or equal to b, and this is also equals to integration over a to b fx dx. And again, if we put and similarly, we can find the probability value of a less or equal to x less or equal to b, or a less than x less than b, and this, and in a probability density function, the value of this probability is equals to integration over a to b fx dx, and this is equals to fb minus fa. So in a probability density function, the interval a less or equal, this is the closed interval. So in a closed interval, the probability value, in a half open interval, the probability value, or in a open interval, the probability value are all same. That means integration over a to b fx dx, and this is equals to fb minus fa. So where fx is the probability density function. But in a discrete case, these four values are not equal. That means integration over probability of a less than x lesser equal to b, and this is equals to fb minus fa. But probability of a lesser equal to x lesser equal to b, this is not equals to fb minus fa in a discrete case. But in a continuous case, these four probability values are equal. Okay, and it is equals to fb minus fa. That is integration over a to b fx dx, where fx, the probability density function. So it will be happen only when the function fx is a probability density function, as well the function is continuous in the interval a to b. This is the second properties of probability density function. Okay. So after that we will talk about some important continuous distributions. Okay. So first we will take the uniform or rectangular distributions. So this distribution is the continuous distribution as well. So it is a continuous distributions, and with a probability density function fx, okay, small fx, and it is given by fx is equal to 0 when x is less than a and x is greater than a, and it is equals to 1 by b minus a when a lesser equal to x lesser equal to b. So in that interval, the functional value fx is equal to 1 by b minus a, and otherwise it is equals to 0, and where fx is the probability density function of the uniform or rectangular distributions. Okay. So where a and b are both are the real numbers, and b is greater than a, and the two parameters of these distributions. So here a and b are the two parameters of these distributions. So from this uniform distributions, we will observe that since b greater than a, so from this we'll get the functional value. So from this we'll get the probability density function fx is greater than a. Fx is greater than 0 in the interval a lesser equal to x lesser equal to b. So in that interval, the functional value fx, that means the probability density function, is greater than 0. And integration over minus infinity to plus infinity fx dx, where fx is equal to 1 by b minus a in that interval a to b. Otherwise this is 0. So minus infinity to plus infinity divided into three parts. The first part is minus infinity to minus infinity to a fx dx, a to b fx dx, plus b to infinity fx dx. But in the interval a to b, the probability density function, it will be 1 by b minus a, otherwise 0. So therefore the integral value minus infinity to plus infinity fx dx, and it will be integration over a to b 1 by b minus a fx, 1 by b minus a into dx. So after integration we'll get, and after integrating we'll get the value of this integration, and it will give 1. So these two are the fundamental properties of the density function. So uniform or the rectangular distribution satisfied these two fundamental properties. The first one is fx is greater than 0 in that interval, and integration over minus infinity to plus infinity fx dx, and it will give the value 1. So after that we'll take one more important continuous distribution, and this is called a normal distribution. That is a very important distribution for the continuous case or the continuous distributions. So it is a continuous distribution. So its probability density function fx, and it is given by fx is equal to 1 by root over of 2 pi into sigma into e to the power of minus of x minus m whole square by 2 sigma square, where x is lies in the interval minus infinity to plus infinity. So this is the called a normal distributions. Okay, so where fx is the probability density function, and it will give this. So where m and sigma being two parameters of the distribution function, and from this normal distribution we'll observe that since sigma is greater than 0, so from this this will get fx is greater than 0 in the interval minus infinity to plus infinity. And the second properties of the fundamental theorem of continuous distribution, it will give minus infinity to plus infinity fx is equal to 1. So in a normal distributions, the integration over minus infinity to plus infinity fx dx is equal to integration over minus infinity to plus infinity 1 by root over of 2 pi sigma into e to the power minus x minus m whole square by 2 sigma square into dx. Okay, so this is the probability density function for the normal distributions, where sigma and m are the parameters, where m is greater than 0. So now we take x minus m by root over of pi into sigma, and this is equals to say z. Okay, so from this integration we'll get, and when we put x is equal to infinity, and from this we'll get z is equal to infinity, and x is equal to minus infinity, we'll get z is equal to minus infinity. So the limit will remain same for the z variables, and this integral value will change, and it will be integration over minus infinity to plus infinity 1 by root over of 2 pi into sigma into e to the power of minus z square into dz. So 1 by root over of pi, it is actually the constant term. So 1 by root over of pi into integration over minus infinity to plus infinity e to the power minus z square into dz. And this is the improper integral of, and this is the gamma function. So integration over 0 to infinity, this is not a minus infinity. So 0 to infinity e to the power minus z square, and it will give root over of pi. Okay, so applying the gamma function, we'll get this root over of pi. So from this we'll get 1 by root over of pi into root over of pi, and after cancelling that term root pi from numerator and denominator, and it will give 1. So the function f of x is greater than 0 in the interval minus infinity to plus infinity, as well as the integration over minus infinity to plus infinity fx dx, and it will give the value 1. So the normal distribution will satisfy. So the normal distribution is satisfied the two fundamental properties of the continuous distributions. The first one is fx is greater than 0, and integration minus infinity to plus infinity fx dx, and it will give 1. So these two functions I have already discussed. So that is uniform distributions and the normal distribution. Both are the probability density function, and both are satisfied the fundamental properties of the continuous distribution function. So after that we are going to discuss about the transformation of the random variables. So in that section where the two variables are present, so let capital X be the random variable defined on an event space capital S. Okay, and S is the the sample space, and let Y is equal to G of X is also the random variable defined on S. So in continuous case, if fx of x and fy of y both are the corresponding density function, so in that case where fx of x and fy of y both are the continuous density functions. Okay, so then fy of y is equal to fx of x. This is actually the theorem on the transformation of a random variables. So fy of y is equal to fx of x into dx by dy within modulus. So provided y is equal to g of x is a continuous differentiable functions. So here is the proof of this theorem. So since y is equal to g of x is a continuous differentiable function, okay, so either dy dx is greater than 0 or dy dx is less than 0, which means y is equal to g of x is either strictly a monotonic increasing function or monotonic decreasing function. So in that case where the function y is equal to g of x is a strictly monotonic, so from this we will get the value of x, and x is equal to g inverse of y, so which is exist uniquely. Okay, so this inverse function is also exist. So now we will take the two cases. The first case is where dy dx is greater than 0, and the second case it will be dy dx is less than 0. So when dy dx is greater than 0, so y is equal to g of x is a function, and it is a strictly increasing function, monotonically increasing, and hence x is equal to g inverse of y. So this is the inverse function, and it is also exist, so this function is also the monotonic increasing. So when x is less than small x, then from this definitions of this, then from this we'll get g of x is lesser equal to g of small x, and where g of x is a monotonic increasing function. So if capital X is less than small x, then from this we'll get g of x is lesser equal to g of small x, that is y is lesser equal to small y. So hence probability of x is lesser equal to small x, and this is equals to probability of y is lesser equal to small y. Okay, so that is fx of x is equals to fy of y. So fx of x and fy of y both are the distribution function of x and y. So now we differentiate on both, we will get dfx of x is equal to df of y. So from this we will get df of y, and it will give fy of y dy, and dfx of x it will give fx of x dx. Okay, and from this we will get fy of y dy is equal to f of x, and this is equals to fx of x into dx by dy into dy. So after cancelling the term dy on both, we will get fy of y is equal to fx of x into dx by dy, and we can write this equation number 1. So similarly, when dy dx is less than 0, then y is equal to g of x is the the monotonic decreasing function. So in that case we will get similarly fy of y is equal to minus fx of x into dx by dy, and we can write this equation number 2. So from equation 1 and 2 we will get fy of y is equal to fx of x into modulus of dx by dy. So hence the proof of this theorem, and this theorem is actually the transformation of the random variable. So here the probability density function fy of y and fx of x both are the probability density functions in the different variables, that means in respect to x and in respect to y, and where y is equal to g of x is the function, and it is either monotonic increasing or monotonic decreasing. So in both cases where the relation, it will be fy of y is equal to fx of x into dx by dy. Okay, and you know where y is equal to gx is the continuously differentiable function. So this is a theorem on transformation of random variable. So after that we will talk about some examples on the continuous distributions. So here is the example. This is the first example. Determine the value k such that fx defined by fx is equal to kx into 1 minus x in the interval 0 to 1 and 0 elsewhere. So is a probability density function, and the second one, find the corresponding distribution function. So from this we'll first of all we will find the value of k from this density function, then we will find the corresponding distribution function. So here is the solution of the given problem. So since the function fx is a probability density function, this is the probability density function. So you know there is a properties of the probability density function. So first property, it will be fx is greater than 0, greater or equals to 0, and the second property, it will be integration over minus infinity to plus infinity fx dx is equal to 1. So in that case we will take the second property, that means integration over minus infinity to plus infinity fx dx is equal to 1. So where fx is equal to, you know, kx into 1 minus x in the interval 0 to 1 and 0 otherwise. So now this integration will divide it into three parts. So first one, say minus infinity to 0 fx dx, second part it will be 0 to 1 fx dx, and third one it will be 1 to infinity. So in the interval 0 to 1, the functional value will give kx into 1 minus x, and in the other interval the functional value is 0. So eliminating the other two intervals, that is minus infinity to 0 and 1 to infinity, then from this integration it will give integration over 0 to 1 into kx into 1 minus x into dx, and this is equals to 1. Okay, so here k be any constant term. So after integration it will give, you know, k into x square by 2. After multiplying by x on the first bracket, we will give x square minus x to the power x minus x to the power 2. After integration we will give x square by 2 minus x to the power 3 by 3, where 1 is the upper limit and 0 is the lower limit, and this is equals to 1. So after putting the value of upper limit as well as lower limit, so from this equation it will give the value of k, and k is equal to 6. So the value of k is equal to 6, where the function fx is a probability density function. So therefore the function f of x, that means the probability density function, it will be fx is equal to, after putting the value of k, 6x into 1 minus x in the interval 0 to 1 and 0 elsewhere, that means otherwise. This is the probability density function after putting the value of k. So now you are going to find the corresponding distribution function of the given probability density functions. So again, the corresponding probability distribution function, it is denoted by, you know, etal f of x, and is given as follows. So you know, when x is less than 0, that means minus infinity to 0. So the functional value in a probability density function, f of x is equal to minus infinity to 2x fx dx. So in that interval the functional value is equal to 0, you know. So 0 into dx is equal to 0. So now we will take the interval 0 to 1. So in the interval 0 to 1, the functional value fx is equal to minus infinity to x fx dx. So this interval divided into two parts, minus infinity to 0 fx dx plus 0 to x fx dx. So in the interval minus infinity to 0, fx is equal to 0, you know, the functional value is 0, that is the probability density function is 0 in the interval minus 1 to, in the interval minus infinity to 0. So 0 plus integration over 0 to x, and in that interval the functional value is 6x into 1 minus x into dx, and after integration it will give the value, and it is equals to x square into 3 minus 2x. Okay, So this is the distribution function in the interval 0 to 1. So after that we will find the distribution function in the interval 1 to infinity. Okay. So in the interval 1 to infinity, the functional value fx is equal to minus infinity to x fx dx. So this interval divided into three parts. So either first one is minus infinity to 0 fx dx plus 0 to 1 fx dx plus 1 to x fx dx. So in the interval minus infinity to 0 fx dx is equal to 0, you know, if the function, the density function is 0 in that interval. 0 to 1 fx dx, it will be 0 to 1 6x into 1 minus x into dx. So in the interval 0 to 1, the functional value will give 6x into 1 minus x. And the interval 1 to x, that means when x is greater than 0, the functional value, that means the probability density function is equal to 0. So this interval will divide into three parts, and from this we will get only the second integration, that means 0 to 1 into 6x into 1 minus x into dx. And after simplifying this integration, and it will give 3x square minus 2x to the power 3, where the upper limit is 1 and lower limit is 0. And from this we will get the value, and it will give 1. So therefore the distribution function f of x, capital Fx, it will give 0 in the interval minus infinity to 0, x square into 3 minus 2x in the interval 0 to 1, and 1 when x is greater than 0, that means the interval 1 to infinity. Okay, so this is the probability distribution function of the given density function. So after that we will talk about the second example on the probability density functions. So here the probability density function of the random variable capital X is fx is equal to k into x minus 1 into 2 minus x in the interval 1 to 2 and 0 elsewhere. This is actually the similar problem like the problem number 1. So determine the value of k. Next we determine the distribution function of f of x, and after that determine the probability of 5 by 4 lesser equal to x lesser equal to 3 by 2. So find the value of this probability. Okay. So since so here is the solution of the given problem. So since the function fx is the probability density function, so from the definition of the properties of the probability density functions, minus infinity to plus infinity, fx dx is equal to 1. So integration over minus infinity to plus infinity, and here fx is equal to, you know, k into x minus 1 into 2 minus x in the interval 1 to 2. Otherwise it will be 0. So minus infinity, so this integral value, so this integration will divide it into three parts: minus infinity to 1 fx dx, 1 to 2 fx dx, and 2 to infinity fx dx. So in the first integration, minus infinity to 0, the functional value, that means the probability density function will give 0, and in the interval 2 to infinity it will give also 0. So this integral value will reduce to integration over 1 to 2 k into x minus 1 into 2 minus x into dx, and it will give 1, and it is equals to 1. So you know, k is a constant term, and after multiplying these two factors, and from this we will get 3x minus x square minus 2 into dx is equal to 1. So now integrate this function, and after integration it will give k into 3 into x square by 2 minus x to the power 3 by 3. This is the integration of x square minus integration of 2 is equal to 2x, where the upper limit is 2 and the lower limit is 1, and this is equals to 1. So after calculation, so after putting the value of upper limit and lower limit, and from this we will get the value of k, and it will give 6. So after putting the value of k, the given problem or the given probability density function, it will give fx is equal to 6 into x minus 1 into 2 minus x in the interval 1 to 2 and 0 elsewhere. So this is the probability density function. Okay, after putting the value of k. So obviously f of x is greater or equals to 0 for all values of x. So after that we are going to find the probability distribution function. So you know the probability distribution function for the continuous case fx is equal to minus infinity to x ft dt. This is the definition of the distribution function of continuous case. So in the interval minus infinity to 1, f of x is equal to minus infinity to x ft dt. So in that interval, the functional value, that is the probability density function, it will give 0. So minus infinity to x 0 into dt, and it will give 0. So now we will take the interval 1 to 2. So in that interval, the functional value will give minus infinity to x ft dt. So this integral, this integration divided into two parts. So first one is minus infinity to 1 ft dt, and second one is 1 to x ft dt. So in the interval minus infinity to 1, ft dt is equal to 0. You know the function, the density function f of t in that interval is 0. So minus infinity to 1, 0 into dt. But in the interval 1 to 2, the functional value, that means the density function, it will give 6 into t minus 1 into 2 minus t. So therefore 1 to x into 6 into t minus 1 into t 2 minus t into dt. So from this integration, it will give 0 plus 6 into 1 to x, and after simplifying, it will give 3a t minus t square minus 2 into dt. Now integrate this function, and it will give 6 into 3 into t square by 2 minus t to the power 3 by 3 minus 2t. This is actually the integration of t square and 2, okay, where the upper limit is x and lower limit is 1. So after putting the value of upper limit as well as lower limit, and it will give 9x square minus 2x to the power 3 minus 20 minus 12x plus 5. And for x is greater or equals to 2, the functional value, it will be minus infinity to x ft dt. And in that case, the integration will be divided into three parts. First part, it will be minus infinity to 1 ft dt. Second part is 1 to 2 ft dt. And third part, it will be 2 to x ft dt. So in the interval minus infinity to 1, the functional value, that means the density function, will give 0. In the interval 1 to 2, the distribution function will give 6 into t minus 1 into 2 minus t into dt. This is the probability density function in that interval. And in the interval 2 to x, the probability density function will give 0. So the first integration and the third integration will give the value 0. And from this, so from the above integration, it will give 0 plus integration over 1 to 2, 6 into t minus 1 into 2 minus t into dt plus 0. And after simplifying this integration and putting the value of upper limit as well as lower limit, and it will give the value of this integration, that means 1. So the functional value, that means the probability distribution function fx is equal to 1 when x is greater or equals to 2. So therefore the distribution function f of x, and it is equals to 0 in the interval minus infinity to 1, 9x square minus 2x cube minus 12x plus 5 in the interval 1 to 2, and 1 when x is greater or equals to 2, that means 2 to infinity. Okay, so this is the distribution function of the given problem. And the third part, it will be find the probability of 5 by 4 less or equal to x less or equal to 3 by 2. Okay, so you know this is the probability of the event, and this event, that means, so this is the definition of the probability or the probability distribution function, probability of a less or equal to x less or equal to b, or the properties of the distribution function of the continuous case. Probability of a less or equal to x less or equal to b, and it will give fb minus fa. So you know probability of 5 by 4 less or equal to x less or equal to 3 by 2, and it will give f of 3 by 2 minus f of 5 by 2. So f of 3 by 2, that means 1.5, and 5 by 4, and it is also the 1 point something. Okay, so the two values of the function f so lies in the interval 1 to 2. So the functional value, that means the distribution function f of x at the point x is equal to 3 by 2, it will give this, and at the point 5 by 4, it will give this. Okay, and in both the values are in the interval 1 to 2. So after simplifying this, it will give 11 by 32. So the probability of 5 by 4 lesser or equal to x lesser or equal to 3 by 2, and it will give 11 by 32. Understood? And after that we will take one more examples on the continuous distributions. So here is the example. So that the function fx is given by fx is equal to x in the interval 0 to 1, k minus x in the interval 1 to 2, and 0 elsewhere. Okay. This is a probability density function for a suitable values of the constant k. Construct the distribution function of the random variable x and compute the probability that the random variable x lies between 1 by 2 and 3 by 2. So from this there are three parts of this question. So first part we will find the constant value k. The second part it will be the distribution function, and the third one the find the value of the probability in between 1 by 2 and 3 by 2. So here is the solution. So since the function f of x, that is this one, is a probability density function, so from the definition you know minus infinity to plus infinity fx dx is equal to 1. So this interval divided into minus infinity to 0 fx dx plus 0 to 1 fx dx plus 1 to 2 fx dx plus 2 to infinity fx dx is equal to 1. Each of the sub interval the function is continuous, and the value of fx in the interval minus infinity to 0 it will give 0, 0 to 1 it will give ox, 1 to 2 it will give k minus x, and 2 to infinity it will give 0. Okay, so after simplifying this integration it will give integration of 0 to 1 x into dx plus 1 to 2 k minus x into dx is equal to 1. And from this we will get x square by 2. So the integration of x is equal to you know x square by 2, where upper limit is 1, lower limit is 0, and integration of k minus x it will give kx minus x square by 2, where upper limit is 2, lower limit is 1, and this is equals to 1. So after putting the value of upper limit as well as lower limit, and from this we will get the value of k, and it will give k is equal to 2. So after putting the value of 2 in the above density function, and it will give you know fx is equal to x in the interval 0 to 1, 2 minus x in the interval 1 to 2, and 0 elsewhere. So this is the probability density function where k is equal to 2. Also f of x is greater or equals to 0 for all values of x. So for k is equal to 2, the fx is a possible density function. And after that we will find the probability distribution function fx, and you know fx is equal to probability of x lesser or equal to small x, and this is equals to minus infinity to x ft dt in a probability density function. Okay, or for a continuous case. So for the interval minus infinity to 0, the probability distribution function fx is equal to minus infinity to x ft dt, and it will give 0. You know the density function in that interval is equal to 0. So the whole integration is equal to 0. Now we are going to find the distribution function in the interval 0 to 1. So in that interval 0 to 1, the distribution function fx is equal to minus infinity to x ft dt. So this integral value will divide it into two parts, minus infinity to 0 ft dt and 0 to x ft dt. So you know minus infinity to 0 ft dt is equal to 0, where the density function ft is 0 in that interval, and you know in the interval 0 to 1 the distribution function it will be x. Okay, so from this we'll get the value of the distribution function, and it will give x square by 2. So after that we will take the interval 1 to 2. So in that interval the distribution function fx is equal to minus infinity to x ft dt. And this interval, that means minus infinity to x divided into three parts. So first part it will be minus infinity to 0 ft dt, second part it will be 0 to 1 ft dt, and third part it will be 1 to x ft dt. Okay, so in the interval minus infinity to 0 the functional value is 0, in the interval 0 to 1 the functional value is t, that means x, and in the interval 1 to x the functional value it will give 2 minus t. These are actually the density function. Okay, in each of this interval. So the first integration, it will give 0, and the integration of t is equal to t square by 2, where the upper limit is 1, lower limit is 0, and from this we'll get the value of integration, and it will give us 1 by 2. And from the third integration, it will give 2t minus t square by 2, where upper limit is x and lower limit is 1. And after simplifying it, it will give 2x minus x square by 2 minus 1. So this is the probability distribution function in the interval 1 to 2. And when x is greater or equals to 2, then the distribution function fx is equal to minus infinity to x ft dt. Okay, this is the definition of the distribution function, And in that case, where the interval minus infinity to x divided into 4 parts. First one is minus infinity to 0 ft dt. Second one is 0 to 1 ft dt. Third one is 1 to 2 ft dt, and fourth one is 2 to x ft dt. So in a question there the functional value, that means the density function divided into 4 part. Okay. So first part, in the interval 1 to 0 to 1 it will be x, 1 to 2 it will be 2 minus x. Okay. So in that case, so that's why this integration will divide it into 4 parts. So first part it will be minus infinity to 0. So in that interval the density function is 0. 0 to 1, in that interval the density function is t. 1 to 2, in that interval the density function is 2 minus t, and 2 to infinity, in that interval the density function is 0. So after that after that it will give the value of this integration, and it will give 1. So therefore the distribution function fx, capital Fx, is equal to 0 in the interval minus infinity to 0. Okay, and it is equals to x square by 2 in the interval 0 to 1, and fx is equal to 2x minus x square by 2 minus 1 in the interval 1 to 2, and fx is equal to 1 in the interval 2 to infinity. So this is the distribution function of the given probability density functions. And the third part, it will be find the probability of 1 by 2 less than x less or equal to 3. So in a continuous case, half less or equal to x less or equal to 3, and it will be equals to half less than x less than 3 by 2. That means the closed interval or the open interval are the same in the continuous case. So from this it will give f of 3 by 2 minus f of 1 by 2, or integration over 1 by 2 to 3 by 2 fx dx. You can take any one of these two. Either probability, you can take probability of 1 by 2 less than x less than 3 by 2, and it is equals to f of 3 by 2 minus f of 1 by 2. And I have already mentioned in the previous examples. And in that example, we will take the integration. So in that interval, the integration is 1 by 2 to 3 by 2 ft dt. Okay. So here, 1 by 2 to 3 by 2 divided into 2 parts. So the functional value into are not same in that interval. Okay. So half to 1 x into dx. So in that interval, the functional value, that is the density function, is x. And 1 to 2, that means 1 to 3 by 2. In that interval, the density function, it will give 2 minus x. And after integration and putting the value of upper limit as well as lower limit, it will give the probability of this, that is the probability of that interval, and it will give 3 by 4. Okay, this is the third part, the probability of value in between 1 by 2 and 3 by 2 for the given problem. I will stop here. Thank you.